So if we've chosen the plot method for inventorying forest carbon, let's get down to basics in terms of what we're talking about here and how to use a spreadsheet to do this kind of work. So this really comes down to a fundamental question of just saying, hey, what's in a plot? How do we measure each piece of carbon that's in that plot and add it all together? So there's a cartoon here on the lower end showing proportion of carbon stock and in some forest carbon pools from a different project. And you can see in that particular project, the relative proportions of carbon in different forest carbon stocks. Notice that the amount in dead wood and litter in that project was especially low, but the large amounts of carbon are in living biomass and in soil organic matter. The same is generally true in Northwest forests, though it'll be a little different since we have large amounts of coarse woody debris that could be, twice the amount of carbon that is represented by this cartoon. Here's another cartoon from a totally different project. And this cartoon is representing both the fluxes in gray and the pools of carbon in white boxes. And again, you can kind of see these different components. So one way to think about our goal in terms of getting a carbon inventory of a stand is we're trying to come up estimates separately for each of these white boxes. How much is in trees, how much is in herbs and understory plants, how much carbon is in soil organic matter, how much is in litter, how much is in down wood, etc. So let's start with the trees. This is probably our biggest pool outside of soil carbon. Soil carbon is a very large pool, and we'll deal with that in a separate video. Soil carbon is a very large pool, but it's not a very dynamic pool. So it's not changing year to year as much as, say, tree carbon might. All right, here we go. In order to estimate tree carbon, we've talked about these biomass estimation equations. Generally, these equations have a form that is somewhat curvilinear, looking something like the graph in the center here, where if you take diameter of a tree on the x-axis, you can predict the mass of a tree on the y-axis. Nothing that's rocket science about this. A larger tree weighs more, and different trees have different wood densities and different properties that make them weigh differently as you increase their size. So there's a different relationship with size. There are giant databases out there for a variety of biomass estimation equations that have been built for different plant species. And I say plant species because not just trees. So in the background here, I'm showing you a small text snapshot of the Biopack database, which is a database that was put together in Oregon, but compiling plant species from all over the place, different equation forms, different species, estimating different components of plant biomass. There's over 1,000 entries in this database. So if one were really diligent, you could go through and match up each individual species that you have in your forest plot with the best biomass estimation equation published in this database. And in the database, there's even links to the official source papers. However, some people have done you a favor. On this slide, I'm showing an example of the work of Jennifer Jenkins et al., who have put together a series of equations that are national scale for estimating biomass based on kind of growth form of trees. So we can lump all the Douglas fir equations together and form one Douglas fir equation. But we can also lump together maple, oak, hickory, and beech into one equation and call that one equation. So that's the top dashed line. We can lump all pine species together and call that one equation. So by combining species that are similar in terms of their wood density and their growth properties, we can form estimation equations that are really pretty good, but keep us from having to go to the individual species level and the individual local level. So this is a generalized approach that's been used in a lot of carbon models now, taking a general biomass estimation equation for a species type and applying it broadly. There are multiple equation forms out there for existing biomass estimation equations, and they're very diverse. And so the other thing that Jenkins et al. Did is they condensed equations into just one form. So we'll end up working with just one form of an equation rather than all sorts of different types of equations, as you can see here up in the table 6 that's represented. at the top of the screen. These are some screenshots of the carbon forest spreadsheet, which you should fill out for your individual plots. In the carbon forest spreadsheet, I've gone ahead and linked individual pages that represent different components of forest carbon. So we'll start with tree carbon. Tree carbon here is represented in the sheet that is larger. I have a plot number, a date it was surveyed, collectors, and then I have a tag number for the individual trees that are tagged, the species, and then the DBH in both the diameter at breast height, or 1.37 meters in both inches and centimeters, height if you have it, and then the biomass estimation. So first, biomass is estimated in kilograms based on the Jennifer Jenkins equations. And so in table 1 here, which is pasted into the document, you'll see the biomass equation form. You will see the individual parameters for that biomass estimation form. And in order to estimate biomass, you plug those parameters into this equation, beta naught plus beta prime times the natural log of dBH. This is all e to the power of, and then we end up with biomass. So exp is just an exponential function. It turns out that's also the form of that equation that you will use in Excel. So in Excel, you can write equals exp and then enter the value for beta naught and beta prime. For example, if I'm looking at aspen or alder, I would enter negative 2.2094 for beta naught and 2.3867 for beta prime, times the natural logarithm of the dBH for an individual tree. In the case of the first alder here on the screen, the biomass that results from that equation, and the dBH is entered in centimeters, is 327.697 kilograms. Converted to carbon, I take 50% of that value, and there you have it. And so we've done that for all our trees. That's our tree biomass. So take a look at that spreadsheet, take a look at the equations in it, and make sure it works for you. Try entering your tree data and see what your total stand carbon comes out like. On the very first page, on the very first tab of the total of the carbon forest sheet, you'll see there's a place to enter your plot number, your plot size, and then there's a calculation of tree mass that is automatic. So it should automatically gather your tree mass in carbon and convert it to carbon per hectare if you enter the values of biomass of dBH and biomass estimation equations correctly. You'll have to tailor each biomass estimation equation to each individual species that you're working with. So you're going to have to go in and change the beta naughts and beta ones, which should help you work with a complex spreadsheet. There's also a sheet here for understory. And so in the understory sheet, you'll see in gray, there's a location here for you to enter your raw data for your understory counts and percent cover. And then there is a series of calculations that take place in the light green area, where by species, based on the percent cover of each species, we can estimate the biomass of those species in your plot. So all you have to do is enter your data here on the sheet in gray, and then go through and enter your percent cover in the data by species. And it will automatically calculate for you the tons of carbon per hectare. Again, it'll put that on that front sheet on at the front of the carbon forest spreadsheet. Similarly, for down woody debris, if you enter your dimensions in especially metric units there, then it can calculate the volume and the mass and the carbon associated with your down woody debris. Something similar will happen for snags. One note though, you'll note that it asks in teal here for the density of that material, and you'll see some example densities here. Getting the density of your down woody debris is a little bit more complicated because we have to use some lookup tables in order to figure out what the density of our down woody debris is. Fortunately, some people have done this work for you, and you'll see a tab labeled DWD-snag density table. In this table, you can try to look up a species that is the closest as possible to each of your downwoody debris or snag species. And then you can see, based on their decomposition code, we can estimate their density. So that's a nice feature. You'll see two separate tables here. One of them coming from Hartman and Sexton, 1996, and another one coming from an FIA report. So in each of these, you'll find some good estimates for density, and go ahead and use those densities to estimate the density of biomass in your downwoody debris, and enter the appropriate values on the spreadsheet. All of this ultimately comes down to taking each component of the carbon in a forest ecosystem and then summing it up. So in this sheet, this is the front page of the carbon forest spreadsheet. You can see that each row is dedicated to a different component of carbon in the system. And then I put in a graphic here to kind of illustrate that. And then ultimately that all sums up to tell you how much carbon you have in a system per hectare or per acre. It turns out for this D8 plot, I actually have a very similar amount of carbon per hectare as is represented in the graphic here, which has 80 tons per acre, and we have about 190 tons per hectare in that plot. Or we did at one time. Just like in this graphic here, we're just simply putting numbers here. And when you put all of your plots together, we can calculate an error around those estimates of carbon. So from all of your plots together across the entire network of permanent plots, we can calculate a mean, and we can calculate standard deviation that would be equivalent to coming up with a mean and standard deviation for all of these components of carbon, which allows us not only to understand how much carbon we have, but we can also understand how variable it is. Okay, the big black box of carbon, that's it.